Hi there. So today we're going to look at really what differentiation is all about, and that's taking real life examples and finding the maximum capacity or the maximum something or the minimum funding or something where it's used in real life. We model with differentiation all the time. And I'm going to start by looking at example 22, which you should be able to see here. It says a large tank in the shape of a cuboid is made from 54 meters squared of sheet metal. The tank has a horizontal base and no top. The height of the tank is x meters. Two opposite vertical faces are squares. Show that the volume v meters cubed of the tank is given by v equals 18x minus 2/3 x cubed. So those of you who know me well will suggest that I'm going to draw a diagram. Now it says the height of the tank is x, and it also says two vertical faces, opposite vertical faces are squares. So if I take this as to be one of the squares, then that is x. I know I've got, it's going to be made from 54 meters squared of sheet metal. So my surface area equals 54. And I know it's got no top. So when I'm thinking about what the surface area of this shape is going to be, I know I've got an x squared here and an x squared there, so I've got 2x squared. And then I need to think about, well, I've got this one here which is x times something. The one on the other side would be x times the same thing, and actually under the bottom would be the same again. So that would be plus 3x times, I'm going to call that y. So 3xy, and that equals 54. So what I could really do with knowing is what y is. But actually, if I make y just the subject of this, so 3xy is equal to 54 minus 2x squared, and then so y is equal to 54 minus 54 minus 2x squared all over 3x. Now, do you think it's worth we saying that that is, well, 54 divided by 3x is 18x to the minus 1, and 2x squared divided by 3x would be 2/3 x. So I'm going to say that's what y is at the moment. Now the question asks for the volume. So if I'm looking at the volume, I can see it's going to be the area of this, so it's y times x, area of the base, times the height, so x times y, so that's x squared y, which is x squared times 18x to the minus 1 minus 2/3 x, which means that the volume is 18x minus 2/3 x cubed, and that is what we're looking for. Now, question B, which you can see now, says given that x can vary, use differentiation to find the maximum or minimum value of v. So how does v change when x changes is dv by dx. So I'm going to say that is 18 minus 2x squared. When I differentiate that, the x disappears, this becomes a 2, and we times by 2/3 by 3 to give 2x squared. We're looking for a maximum and minimum, so that's when dv by dx equals 0. So it's not getting any bigger, it's not getting any smaller at that point in time. So 18 minus 2x squared equals 0. So 2x squared equals 18. So x squared equals 9. So x equals plus or minus 3. I think probably at this point we should realise that minus 3 has an irrelevant meaning. We can't have a negative side length of a cuboid, that would be just nonsense. So x equals 3. And so we go back to looking at v to answer the question. V equals 18x minus 2/3 x cubed. So that's 18 times 3 minus 2/3 times 27. So that's 54. Take away 18, which is 36 meters cubed. Now question C then goes on from there to say, justify that the value of V you have found is a maximum. So we need to find that it's a maximum, so I'm going to look at d2V by dx squared, second differential. So I differentiate 18, that disappears. I've got minus, and then the 2 comes down and reduce the power by 1, so that's minus 4x. So I know that x equals 3. d2v by dx squared is equal to minus 4 times 2, which is minus 12. And as that is negative, V is a maximum. So very, very typical problem. I particularly like this. The idea that there was a bit in there that you didn't know how to find, and that was that length there, which was so important to find in the volume. But the fact that they'd given you the surface area gave you the clue. You had to work through the surface area, so that would help you find what that value was. Then you could progress on to working out the volume and to get me that. And then once this is like the modelling bit, working with the model to find the actual relationship of the volume, and then we're into the differentiation. So differentiate, put equal to 0 will give you the value of x, which will give the maximum or the minimum. Put that value of x in to see what the maximum and minimum value is, and then justify that as a maximum is so common. So common. So lots of things there that are important to know, and particularly in the realms of what do you do when there's something you don't know. Use the information that you're already given. It will not be ever that you don't know how to work this out, or you're not given enough information to work it out. So hopefully you'll find that interesting, and the exercise that you're doing today to be a nice challenge. Before we finish, number 1 recommendation, where you can draw a diagram. It helps you plan out so much and think about the way you structure your work. Okay, speak to you soon. Goodbye.